This video is going to have a look at scatterplots and lines of best fit and how we can apply our linear equation to determine that equation for the line of best fit and make predictions. So by the end of the video, you will be able to find the equation of a line of best fit and then use it to be able to make a prediction of what a value is going to be based on our line of best fit. When we've got bivariate data, so we've got an independent and a dependent variable, and we've placed that information onto a scatter plot, we can fit a line of best fit by eye. So that means having a look, trying to get the lines. So we've got an equal amount of points on our scatter plot, either above and below the line. So this would be called a line of best fit, or sometimes you may hear it or see it referred to as a regression line, which means the same as a line of best fit. Once the equation of the line of best fit has been found, it can be used to make predictions about the variables. So the steps for finding the equation of the line of best fit: if the question hasn't given you a scatter plot, draw a scatter plot with the independent variable on the x-axis and the dependent variable on the y-axis. So you need to make sure you have a scatter plot to start off with. Sometimes it'll be provided to you in the question. Other times you will need to draw one yourself. Then draw in your line of best fit on the scatter plot, remembering you want about the same number of points above and below your line of best fit. After you've got your line of best fit, you can select 2 points along the line and then use it to find the gradient. You can also find the y-intercept by either reading it off of the line of best fit or substituting in one of your points into the formula. And then once you've got the gradient in step 3 and the y-intercept in step 4, you can go ahead and write your line for the line of best fit equation, which is going to be in the form of y equals mx plus c. So let's have a look at an example of how we can find the equation for a line of best fit. So in the example, the table and scatter plot represents the relationship between test scores in maths and test scores in physics for 10 year 11 students. And a line of best fit has been added in to the scatter plot already. The question is asking us to choose 2 appropriate points that are on the line of best fit and to determine the equation of the line. So first we need to identify the gradient. And to identify the gradient, we need to select 2 points. So the best way of selecting 2 points is trying to identify locations where the line crosses one of the grid lines in the background. So having a look along the line, I can see that it crosses the grid line at 30 and 20 and also at 80 and 80. So I've identified my 2 points and I can write them down, 30, 20 and 80, 80. So to calculate the gradient, I want to label them x1, y1, x2, y2. Then go ahead, gradient equals y2 minus y1 over x2 over x1. So 80 minus 20 over 80 minus 30. So my gradient is going to be 60 over 50, which simplifies to 6 over 5. So my line of best fit in the scatter point, in the scatter plot, has a gradient of 6 over 5. So therefore I know that y is going to equal to 6 over 5x plus c. So step 2 is going to go through and identify the y-intercept. So I can choose a set of points. So I'm going to choose 30 and 20. So when x is equal to 30 and y is equal to 20, I'm going to substitute them into my formula using the gradient. So 20 equals 6 over 5 times 30 plus c. So 20 equals 36 plus c. So subtracting 36 from both sides, c is going to equal to negative 16. So my y-intercept is going to be negative 16. So finally, now that I've got my gradient from step 1 and my y-intercept from step 2, I can go ahead and write the equation. So the equation for my line of best fit is going to be y equals 6 over 5x minus 16. So one thing you can do with this line of best fit is to use it to make predictions. So predictions can also be made graphically by drawing lines from the axis up to the line of best fit or the regression line to see where they form the data points along the axes. There are a couple of types of predictions that you can make. Interpolation involves making predictions within the boundaries of the original data. So where the dots are onto the scatter point will be in interpolation. Extrapolation involves making predictions beyond the bounds of the original data. So you're making a prediction where you haven't got any dots on your scatter plot. Predictions can be considered reliable if they are obtained using interpolation. So where the dots already are on the scatter point, and if you've got a large number of dots around them, you can reasonably rely on those predictions. So having a look, we can see that we have got points up in this area of our scatter plot. So if we're making predictions for test scores between 40 and 90 in maths, those predictions are going to be considered reliable. If we are making predictions outside of that range, then we're extrapolating, and those predictions are not going to be considered reliable. So let's have a look at an example. In this example, we have got data for air temperature and the depth of snow at a popular ski resort. So the line of best fit has already been calculated, and it is y equals negative 7.2x plus 8.4. And it wants us to use our line of best fit in the equation to determine the depth of snow when the air temperature is negative 6.5 degrees Celsius and 25.2 degrees Celsius. Then it wants us to comment on the reliability of the estimates from part A and part B. So let's have a look and do our estimate for part A when the air temperature is negative 6.5. So that is going to be our x value. So we want to substitute in negative 6.5 into our equation for our x value. So negative 7.2 times negative 6.5 plus 84, which equals to 130.8. So the depth of snow when the air temperature is negative 6.5 degrees will approximately be 130.8 centimeters. So now we want to do the same process for part B, and our air temperature is going to be 25.2. So substituting in 25.2 for x, so y is going to equal to negative 7.2 times by 25.2 plus 85, which equals negative 97.44. So when the depth of snow, when the air temperature is 25.5 degrees outside, is going to be negative 97.44 centimeters. So now that we've made our predictions, we need to comment on the reliability of the estimates. So having a look at the first estimate, we were estimating for when the temperature was negative 6.5. So about here on our scatter plot. And we can see that we have got data in that area on the scatter plot. So it is going to be an interpolation, which means we can be reasonably comfortable with the prediction that is made. Having a look at B though, when the temperature was 25.2, we don't have information for when the temperature is 25.2. So this time we are extrapolating, and our prediction is not going to be reliable. Now we can tell that our prediction isn't going to be reliable because it estimated negative 97.44 centimeters of snow. Now we cannot have a negative depth of snow, so that means our estimate is clearly unreliable because we were using extrapolation to make our prediction. So there are a couple of examples of how we can find the linear equation for a line of best fit and then use that equation to be making predictions.